Assalamu alaikum. In today's lecture we are going to find the flux linkage of one single conductor if we have more than one conductors in a group. And this derivation that we are going to do today, it will help us out in finding the inductance of a composite conductor. So today's lecture is actually the prerequisite of the inductance derivation for a composite conductor. So we are going to start the example of a group of conductors in which we have to actually calculate the flux linkage of one particular conductor due to the currents flowing in all of these conductors, right? This is your conductor number 1, this is 2, 3, and we are assuming that there are n number of conductors. And then we also have defined a point P. So for the starting point of the derivation, we are only considering the flux till point P, and the distances from the conductors from for example, conductor number 1 to point P is d1P, from conductor number 2 till point P is d2P, and so on. So what we are considering is that all the conductors are carrying current, and some of these conductors are carrying a current in the forward direction and some are having the current in the reverse direction, but the summation of all the currents is 0. What does it mean? That I1 plus I2 and up to the currents in all the conductors will sum up to 0. So there are some currents in the forward direction, some in the reverse direction, but the summation of all the currents is equal to 0. And at this point P is the point till which we are considering the flux. All the flux beyond P we are not considering in the starting point of this derivation. So if we have to write the flux linkage formula for conductor number 1, this is lambda 1 P1. So for conductor number 1, the flux linkage for conductor number 1 till point P when the current is flowing through the conductor number 1. So this is lambda 1 P1. So lambda is the flux linkage, conductor number 1, flux linkage till point P when the current is flowing through conductor number 1. So this is the flux linkage. And we know that there are two parts in the flux linkage equation. The first one is the flux linkage due to internal flux, and the second one is the flux linkage due to the external flux. And now in numerator, the point is the one that is farther away from the conductor, and in denominator is the point which is closer to the conductor. So we are writing the radius of the conductor from which the current is flowing. So this is the actual formula for the flux linkage, which is having both effect due to the internal flux and due to the external flux. But if we have to write the simplified equation of the flux linkage in terms of fictitious conductor, this particular equation is the one in which we are assuming that we have a conductor of radius r1 dash, and we are just considering the internal flux effect on the flux linkage in this r1 dash value, and r1 dash value is equal to r1, which is actually the radius of the conductor, into e raised to minus 1 by 4. So this particular constant is actually compensating for the internal flux, right? So this is the flux linkage value for conductor number 1 till point P due to the current flowing in the conductor number 1, right? So now if I have to write the equation for the flux linkage with conductor number 1 till point P due to the current flowing in conductor number 2, so this is lambda 1 P2, flux linkage due to the current flowing in conductor number 2 with conductor number 1 till point P. So this is the formula remains the same, 2 into 10 raised to minus 7 I2. So because we are considering the current in conductor number 2, and natural log of d2P, which is the farthest part till point P, and the distance between the conductor number 1 and conductor number 2, right? So similarly we can write the flux linkage formulas for all the conductors with conductor number 1. So this is for conductor number 1 current flowing through the conductor number 1, and when the current is flowing through conductor number 2, when the current is flowing through conductor number 3, and the current flowing through nth conductor, right? So if I have to expand this logarithmic term, there are two terms and both are dividing, so we can write it in terms of multiplication, right? So if this is ln d1p over r1 dash, so we can write it like ln d1p plus ln 1 over r1 dash. So we have two multiplying terms in this natural logarithmic term, so we can write it in the form of a summation. So this is the expansion that we have. So we have just expanded it in two terms. For each of this one term, we have two terms in this particular equation B, right? Now what we want to remove this p term, because this p term is actually limiting our whole derivation till point P, but we know that the flux lines can go up to the infinity, so we have to add all the flux lines in the derivation. So that's why we want to remove this P term or all these P terms from the equation. So we have separated this from the final equation that we want, right? So firstly, we assumed in the start of the lecture that all the currents, the summation of all the current is equal to 0, right? So what does it mean? I1 plus I2 till In is equal to 0. So we have separated out In, and all the terms other than In we have taken it to the other side of the equality. So this is the equation that we get, and now we will replace this In with this equation. Now we are going to solve this equation. So this equation is I1 ln d1p plus I2 ln d2p up to In ln dnp, right? So we are putting the value In is equal to I1 plus I2 plus In minus 1 at this point, right? So this will become I1 ln d1p minus I1 ln dnp plus I2 ln d2p minus I2 ln dnp. Similarly, we will go up to the value of current In minus 1 ln dn minus 1 p minus In minus 1 ln dnp. So now we have two logarithmic terms with a negative sign between them, so we can write these two parts of the equation in form of a fraction. So the equation will become I1 ln d1p over dnp plus I2 ln d2p over dnp, and the last term of the equation will be In minus 1 ln dn minus 1p over dnp. So actually what we are doing, we are trying to remove this part from the equation. So this is the same part, right? So if we have to consider all the flux linkages, so then we have to move the point P till infinity. So what we want to do, we want to actually consider all the flux linkage, and to do so we have to move point P till infinity. So when we are moving point P till infinity, then the denominator term dnp, it will become very large because it has P in it. So the P value is actually infinity now, so the distance from a certain conductor till infinity will be infinity, so dnp will become very large. Similarly, d1p also will become very large. So all these logarithmic terms will become ln infinity over infinity. And now we have to solve this ln infinity over infinity. What we will do, we will put limit x approaches to infinity and replace infinity with x. And we know that this x is infinity, so we can add 1 and it will not make much of a difference. So limit x approaches to infinity is x plus 1 over x, and limit x approaches to infinity, this will become 1 plus 1 over x. And now if we'll replace x with infinity, it will become 1 plus 1 over infinity. So this is 1 over infinity is actually equal to 0. So limit natural log of infinity over infinity is equal to ln 1. Actually there is ln here, so I have missed this term. So this will become ln 1, and ln 1 is equal to 0. So all the terms which are having ln d1p dnp, ln d2p over dnp, ln dnp over dnp, all these terms will become 0. This will be 0, this will be 0, this will be 0. So this term will be equal to 0, and we will only have the flux linkage formula which has no p term in it. So this is the equation that is removed from the flux linkage first equation, right? So what we have done, we have actually moved the point p till infinity, and then dnp will become a very large value, and all the dnp terms which has a natural logarithm dnp terms, they will become 0. So they are removed from the equation, and the total flux linkage due to all the conductors will be lambda 1 in 2 into 10 raised to minus 7 I1 ln 1 over R1 dash, which is the fictitious radius, then d12 due to current number I2 due to the current from the conductor 2, d13 due to the current in conductor number 3, d1n conductor number n. So this is the flux linkage value for conductor number 1 when it is placed in a group of conductor which is having current pass through all the conductors, right? So all the conductors, if we have n conductors, so we have n currents passing through those conductors. So we will be using this formula when we have to find the inductance value for the composite conductor. Thank you.